Checchin. I'm associate scientist in the Superconducting Quantum Materials and System Division. And this is Silvia Zorzetti, and she's an engineer and Bardeen Fellow inside the same division. So we want to talk about quantum computing and what are the activities that we are doing here at Fermilab, specifically in this lab here. So first of all, I wanted to share with you a short presentation to give you like at least a flavor of what is quantum computing and give you like an introduction of what is a quantum bit. And yeah, and that's it basically. So really, really simple and fast presentation. Okay. Can you see the screen? I believe so. Okay.
Yep, it looks good.
Okay, great. No, give me one sec. Okay. So first of all, what is a quantum computer? So to understand what is a quantum computer, we first have to remember everybody what is normal bits. So a bit is the smallest part, the smallest computational part that you have in a classical computer. And a bit, of course, can assume two distinct values. Could be a 0, could be a 1. And if you think about a simple quarter coin, you can imagine that 0, for example, is head and 1 is cross. So at this point, if you think about having a 4-bit register, so with a 4-bit register, you can actually represent a certain amount of numbers. And you can see here with 4-bit register, you can represent a total of 16 numbers. And if you do the math, you can figure out that if you have a number n of normal bits, you can actually represent a total of 2 to the n numbers. So with a quantum computer is kind of different. So in a quantum computer, we have what we call quantum bits, or for short, qubits. So a qubits as well can assume two values, 0 and 1. And so again, could be head or cross. But since it is a quantum bit, it can also assume another type of state that is a superposition of 0 and 1. And to understand this in terms of a coin, you can imagine that you are actually flipping a coin. And while the coin is spinning in the air, at that point, the coin is not either 0 or 1, it is in a superposition of the two states. And so you can in a really simple way, imagine a quantum bit in this way as a type of bits that can assume state 0, state 1, but also a superposition of the two that is basically this spinning coin. So at this point, if I represent a quantum register composed of 4 qubits, you should imagine something like that. So we have 16 registers like this, where in each one, each qubit of the register can assume actually at the same time 0 value and 1 value. So you can then imagine that for each of these registers can assume 16 numbers. And this means that a 4 qubits register can actually represent a total of 256 numbers. So if you do the math, this will be 2 to the 2 to the n, where n is the total number of qubits. So in other words, then with a quantum computer, you can represent a much larger numbers, much larger numbers with a smaller amount of qubits. And you can imagine that then, so what? So what does this means? So let's assume that you want to figure out a password with your PC, and the password is composed by 4 digits. So at this point, with a classical computer, you put inside something like this. So we have a register of 4 bits, and then you start to try each and single numbers one by one inside your computer. So you try the first one, you try the second one. Also, the second one is not good. The third one and the fourth one eventually is going to be your password. So you understood what is your password. You can hack in the computer, but this takes like really long time. Especially if you think about if we have like numbers, really big numbers, that is going to be. There is people that they say that for really big numbers, for the level of cryptography that we have right now, using a classical computer to break in one of those codes is probably going to take the time of the universe. So it's going to be too much. So no way we can do that. Okay, what happens if instead we use a quantum computer? At this point, we throw inside the computer a register that is made by 4 qubits, and this number represents already all the possible numbers that represent your passwords. And your computer is gonna work as if at this point we had 16 computers, and each computer is checking at the same time the password. And this is independent on how big is the number, because we are talking about quantum mechanics and everything is possible in this sense. And so if you think about this, is a much efficient way to do the same problem, to solve the same problem. And therefore, this is like the simplest way to imagine how quantum computing can actually change the world, especially in cryptography, but not only. If you imagine, for example, you want to understand what is the best path to go from point A and point B, a normal computer would simply check every single path one by one, understand where is the traffic light, what is the best solution, but it's going to take like a humongous amount of time. With a quantum computer, you can actually check all the possible routes at the same time and figure out what is the best way in real time. So a problem that is going to take the time of the universe, at this point, is going to take probably a couple of minutes. So this is the powerfulness of quantum computers. So in other words, you could imagine that the parallel processing of the computer is already built in the quantum bit itself. So that is the main powerfulness. So how do we make a qubit? So okay, so a qubit, it's a pure quantum mechanical system. So it is basically a system that can be prepared again in a state 0, in a state 1, or in a superposition of the two. So there are many ways in which we can build qubits, and we're going to see a specific case here, Fermilab, what we do. But for simplistic imagination, you can imagine that we have a particle. In this case, could be an electron, for example. If you are familiar with an electron, I mean, think about an electron. And an electron has a spin, which means that it has its own magnetic field, if you want, in really simplistic way. And so it's going to have a north pole and a south pole. And so you can imagine that if the spin of the electron, so the north pole, is pointing up, you are in the state 0. If the spin of the electron is pointing down, you are in a one state. And in principle, you can prepare the spin of your electron to be in a neutral position, or like in a superposition of the two. And so in this case, we have what we call a superposition state. So this kind of simple system would be a perfect qubit. So at this point, you can imagine how can we control the qubit. Let's assume that we start with a qubit in the 0 state, like this, and we start to apply a perturbation. By applying the perturbation, we're starting to change the state of the qubit. And by perturbation, I mean, for example, an electromagnetic field, could be microwave radiation, could be light, could be, there are many ways on which you can do that. So the main part is that you start to apply the perturbation, and the change or the state of the system change with time. And if you continue to change it, to apply the perturbation, eventually you're going to flip the state of your qubit from 0 to 1. But it is important to point out that there is always a condition in which your qubit is going to pass through superposition of states. So by controlling the length of your perturbation, you can actually deterministically define the state of your qubit, even if it is a superposition of states, not only 0 and 1. So at this point, as I said, I mean, there are like several types of possible qubits. The most used at the moment, I mean, the most studied, I would say, not really used, are what we call superconducting qubits or trapped ion qubits. So superconducting qubits, they take advantage of superconducting materials, and they are at the end a macroscopic type of object. So you can actually pick it up with a hand, but they behave as a quantum object. So as something that is really, really small. And this is something that has to do with the superconductivity, but I'm not going to go in detail with that. So the other possibility instead is trapped ions qubits. So in this case, is something similar to what I was showing here. So we have an ion. So it's basically an atom that is charged, that is actually confined in an electromagnetic confinement, and can be controlled by applying like pulses of light. While for superconducting qubits instead, we're talking about pulses of microwave radiation. So Fermilab has a lot of understanding in microwave and a lot of understanding in superconductivity, because we use superconductivity to build devices to accelerate particles in particle accelerators. So we're really good with that. Before we decided to move forward and apply our knowledge in superconductivity to build superconducting devices that can be used as qubits and to move forward the technology in that area. So superconductivity is basically, superconductivity is a state of matter for which the resistivity of the material goes to zero. So if you take a normal metal and you cool down the metal at really low temperature, the resistance of the metal is gonna reach a certain constant value and it's gonna stay there. For a superconductor, the situation is slightly different. And so the resistance, as soon as you go down in temperature, is gonna reach a temperature that is called transition temperature, at which the resistance drops to zero. And at that point, we are in the superconducting phase of that metal. So you can actually transport current through that metal without having resistance. So that's actually really, really, really important for many applications. And so there are like several metals that are superconducting, and specifically what we use for our devices is niobium, that has this transition temperature at 9.25 Kelvin, so minus 443 Fahrenheit, more or less, and aluminum, that is at transition is a 1.2 Kelvin, so more or less minus 460 Fahrenheit, more or less. So, which means that all the devices that we study here at Fermilab needs to be cooled down at really low temperature. This is not the only motivation why we need really low temperatures to operate the device. The other motivation that is really important is also the following. So let's assume that you have a qubit as this one, and around the qubit there is like some temperature. So temperature at the end is energy. And if you apply temperature to the qubit is gonna change state. And you don't want that, because you want to control the qubits with your own pulses. So if you leave the qubit to interact with temperature, at that point you're gonna lose information. Qubit is gonna flip state, and eventually a 0 is gonna transform in a 1, and you introduce error in your code, and that's not what you want. So at this point, what you wanna do then is to cool down the qubit as cool as you can. And so we use like a specific type of refrigerators, so-called dilution refrigerator that Silvia is gonna talk about later, that can reach temperatures of the order of 10 millikelvin, so minus 460 Fahrenheit. That is actually colder than outer space. It's actually colder than outer space. So outer space temperature is 2.7 Kelvin, and so we are much colder than that. Okay, so how do we measure the state of a qubit? So we have this quantum mechanical object that is really fragile in terms of perturbation from the external environment. So as we see, if we warm up too much, we're going to lose the information. A 0 is going to become a 1. So that's something that we have to be really take care about. So a superconducting state, of course, follows the rules of quantum mechanics. And one of the most important rules in quantum mechanics is the fact that whenever you measure a system, you are perturbing the state of the system itself. And so this can be explained with the thought experiment of the Schrodinger cat. So assume that you pick a cat and you put it inside a box. And inside the box, there is also radioactive material that is decaying. And the radioactivity is actually a quantum mechanical effect of matter. So you can imagine that as soon as you close the box with the cat and the radioactive material inside, at that point, the cat could be either dead or alive. So he's dead if your material actually decayed and killed the cat because of radiation. At the same time, could be alive because maybe the material did not decay yet. So at this point, you have the cat is in a weird state, is in a superpositional state, is at the same time dead and alive. What happened though if you open the box? At that point, does not make sense to have like a cat in a superposition, dead or alive. He must choose. He must choose to be dead or he must choose to be alive. And that is like the beautifulness of quantum mechanics. If you don't do any measurement, your state can be in a superposition. Your system can be in a superpositional state. As soon as you do a measurement, the system we say collapses in one of the two possible states. So in this case, cat alive and cat dead. What does this mean then? It means that if we do a measurement of a qubit, so let's assume that we start with a qubit in the state 0, we apply some perturbation and we prepare the qubit in a superpositional state. So in this case, the qubit is 60% 0, 40% 1. Okay, super weird classically. And now we want to do a measurement and see what is the state of this qubit. We do the measurement. There is no way that we can measure this situation. There is no way, because this is not possible. We cannot measure a situation in which is 60% and 40%, 60% 0 and 40% 1. Actually, what we want to measure is that what we want to do actually is to repeat this experiment several times and repeat the measurement, so that we do several measurements, and over many measurements, we're going to figure out that 60% of the time we're going to measure qubit up, 40% of the time the qubit is going to be down. And so this is actually as important implication. And the most important implication is that the output of a quantum computer is a probabilistic result. So that this is important to point out. I mean, it's really the essence of the quantum computing itself. So because of this factor that use superpositional state, at the end of the day, whenever you run your code and you get your result is going to be a probability of being in one state or in another state. Of course, the probability could be 100% and 0. It really depends on how good you are in writing up your algorithm. So concluding, we learned that a quantum computer is composed by qubits, so quantum bits, and take advantage of quantum mechanics. And a qubit can be in a 0 state, 1 state, or in a superposition of the two. A quantum computer can solve complicated problems that are typically not solvable by classical computers. And the qubit state can be controlled by perturbing it with some type of signal. Could be microwave, could be light, depends on the type of qubit. So if we use superconducting qubits, we need to go to low temperature, and temperature in principle can disrupt the state of the qubit. So we want to go to really low temperature, so 10 millikelvin. And the outcome of a qubit measurement is probabilistic, which means that the quantum computer returns probabilistic results. And that's it from this presentation.
We have a couple of questions.
Yeah.
So from Sydney, how do you get the temperatures that cold?
Okay, so we use a dilution refrigerator that Silvia is going to show. Actually,
yeah, actually it's there.
Okay. So, okay, I can, yeah, I mean, Silvia is pointing out that the dilution refrigerator, if you look to Silvia Zorzetti cam. Okay. So basically, this is a refrigerator where you use two different isotopes of helium. So helium can be in the isotope, what could be like helium-4 or helium-3, depending on how many neutrons you have. So by simply liquefying helium-4 and pumping on the bath, so decreasing the temperature on the bath of the liquid, you can achieve temperatures around 1 Kelvin. To go lower than that, what you want to do is to mix up the two phases. So the two isotopes, helium-3 and helium-4. And because the thermodynamics of the mixing of these two phases requires that you provide heat to have these two phases to mix, you can actually, instead of providing heat, you can simply say, okay, the heat is going to be provided by whatever I'm going to cool. So simply the fact that you are mixing the two phases, this mixing is actually subtracting temperature, so subtracting heat, and so decreasing the temperature of whatever is attached to this device. So this is the principle of functioning of this type of dilution refrigerators.
All right, the next question from Laura. How do you protect the qubits from outside perturbations affecting them?
Okay, so maybe do you want to answer this,
Yeah.
Silvia?
So, yeah, so basically the fact that we cool down the qubit in such low temperature, it's a protection against the interaction with the environment. So that means, you know, millikelvin is a super low. If you think that the water, the ice is at the temperature of 32 Fahrenheit, that is 0 Celsius, and And so basically, we are cooling down things at a temperature that is 1,000 times lower. And theoretically, 0 Kelvin is the temperature that we cannot reach in reality, but theoretically, it is the temperature at which the atoms and the electrons don't move. So the mass is fixed. So this is a very low temperature. And the reason why we go that low is that because this qubit interacts very weakly with the environment. And so we have to protect it and we have to keep the information. And then another way that we use for the measurement is, it is a probabilistic measurement. So we repeat the measurement many times, and in the end, we have something like 99% of fidelity. That means we have, we have a probability 99% to have done the right measurement. However, there is always a 1% possibility that this measurement is wrong, because it is the beauty of quantum computing, as Mattia said. There is always a probability, is kind of superposition, and the probability that you have some states that are not where you want them to be.
Great. There's a couple of questions that I think are related from Braden, and another one that was sent to me directly. So Braden asks, what type of problems do your quantum computers solve? And then the follow-up is, why can a quantum computer solve problems that a classical computer can't?
Okay, I can answer that if you want to.
Yeah.
You can.
I mean, theoretically, there are a lot of problems that cannot be solved classically, or let's say that even if you have a supercomputer, it will take thousands of years to resolve. So, one thing is, to make an example, how many digits are, the number pi, 3.1415, and then it has like an immense number of digits outside. So these kind of problems are kind of difficult to resolve in a classical way. And so, this is where the parallelizing the operation and what Mattia explained, that basically you have a lot more capability with quantum computing, because it's like you do a lot more operation at the same time, because you do them in parallel, you don't do them in series. Then it helps a lot. Okay, maybe another thing I can say. Can you still hear me?
Hey, Amanda, you're muted.
Mute.
Yeah.
That's the first time I've done this. It had to happen eventually.
So another thing I can add is that there are a lot of, now I just said something about, classical mathematics, but there are a lot of other applications. So for example, about quantum chemistry, there is a way that quantum computing can help in making some kind of proteins that are very hard to simulate otherwise. And then another neat application is actually for video makers. And so, there are some algorithms that you can run to augment the quality of a video, of a movie, like what we have a high definition and so on. And it turns out that these algorithms are very complicated and take a lot of computing resources, and this can also be resolved by quantum computing.
So there's some more questions coming in, and they're really great, but I want to make sure you have time to show us all that you want to show us too.
Maybe I can go quickly over there.
Yeah.
Okay, I'll mute this one.
Okay, can you hear me?
Yes, we can.
Okay. Okay, so basically what we show here is the dilution refrigerator, and then Mattia did a nice explanation of why we use this and what it is used for. So I want to show you what we actually cool down. So we cool down objects, it is here. So we cool down some objects like this. So these cavities are not done for quantum computing. These cavities are done for particle accelerator. So basically particle accelerator, the beam pass through, and then here there are many cells, and it gets excited at each cell. It turns out that these cavities are so good that can be used to extend the life of a qubit. Because the actual problem with quantum computing is not the mathematics, but the realization. So the implementation, as I said, this interaction is very weak, and so you need to have something that is very efficient to store the information, and this is something that we can use. And that's what we are trying to do here at Fermilab. Why Fermilab is special is because we have this kind of technology that is the best in the world, and also because the fact of having a 3D device mitigate a lot of noise sources, and also amplify the computing complexity. So you can reach a lot more states that you can do with other kind of devices. So this is something special that we have here. And then maybe just to show you some measurements that we do. So this is, like maybe another question can be, how do you see a qubit? So as Mattia said, you cannot know the state of a qubit until you don't open the box, like the Schrodinger test. So here basically this is what happens. So these lines here is high power. That means is just our common world. So we live kind of in high power world. So here we only see the cavity because the interaction with the qubit is too low at high power. And then when we go down with the power, we see that there is a frequency shift. This shift is the qubit. And we use all these radio frequency techniques to communicate with the qubit and then to know what is the state. And this is again something special that we have here at Fermilab because we develop a lot of expertise and skills in RF and techniques to control the particle accelerator that can be used for quantum computing. Okay, maybe another thing I can show you.
Real quick, because I think the background noise might have cut out a little bit. Someone's asking what the metal object that you were showing before was?
That is a cavity.
Okay.
So that is a smaller one.
Perfect.
So this is a resonant cavity. I mean, to make an example, a can of a Coke, I mean, is a cavity, okay? It's just not an efficient cavity. This is a very efficient cavity. So that means that if you put a signal inside here, it will resonate for 2 seconds, which is a lot. And then this is very small, and this is a qubit actually. So this is what we put inside the cavity, and we make the quantum computation.
And it's so that big refrigeration system is to cool that tiny.
Yeah, because this tiny thing interacts with this big thing very quickly, and so to have an efficient interaction, you need to be at very low noise, and you reach the low noise by the low temperature. So we are going to move to the desk.
So to add to what Silvia was saying, and to get back also to a question that was done before, how do you make sure that the qubit does not interact with the outside environment? So the cavity itself is a really good screen. So that is a superconducting resonating cavity. Has like a really huge quality factor, which means that it behaves like a really nice passband filter. So the frequency of that cavity, the smaller one, was around 9 gigahertz, and you can imagine that the passband filter, so the bandwidth of the filter, is around probably like 0.1 hertz, and the cavity oscillates at 9 gigahertz. So it's like really nice filter that filters out all the electromagnetic radiation that could, in principle, interact with the qubit and screw up the state of the qubit itself. So the cavity is used to control the environment around the qubit, around the qubit, and also for the readout, as Silvia was explaining.
Awesome. Yep. And there's so many great questions. Let's see. can you comment on how quantum is being used for artificial intelligence applications?
Okay, I'm not really the right guy, but as far as I know, I understand the thing. I mean, again, I mean, a quantum computer has this ability of computing at the same time different information all at the same time. So this is actually pretty good in terms of artificial intelligence, because what a classical computer will do is simply, okay, take one possibility, analyze that, and figure out how can improve myself to perform a specific type of instruction, or exactly like a specific type of instruction. And he's going to try each and every possibility in series until he finds the right one, and reiterates the same thing again, changing a little bit the way he was doing before, because he learned meanwhile he was solving like this series operation, and I mean it becomes better in doing that stuff. So with a quantum computer, the powerfulness is that it can solve simultaneously all these different tasks in all the most different ways, and figure out what is the best one. And once he figures out that what is the best one, he can actually apply that way in which he was solving the thing to all the others. And this is done, like, again, in a parallel fashion, without this sequential type of simulation that is typical for classical computer. That's why the powerfulness of the quantum computers also for artificial intelligence is definitely something that they're looking into. I'm not, though, an algorithm guy, so I cannot comment more than this. I'm sorry.
I had someone ask, they noticed that the clock on the wall never moves, and they want to know if you accidentally beamed yourselves into quantum non-time.
That's probably true.
I have a student, Abby, that is asking, what type of degree do you need to work in this lab?
We have like a really different type of degrees. So in my case, I have a degree initially like a bachelor in material science, master in material science, and then a PhD in physics. And indeed, my job is mostly like understanding how to make better device. So you have to work with materials and figure out what is the best material. Silvia instead has a PhD in electronics engineering. So she's mostly instead on how to send signal to the qubit, how to figure out how to measure it. And then there are like other people that only have like degrees in like physics and more concentrated maybe in quantum mechanics, that instead understand how to make communicate to different qubits with each other. So how to entangle them, how to do quantum mechanical manipulation. So it really depends on what you want to do, what you want to do. I mean, in principle, I mean, this specific field is like the merge of really different disciplines, because you don't not only need physicists that do measurement or figure out how to run things. You need physicists with specialization in algorithms, for example, to figure out how to write correct algorithms to be run in quantum computers. You need engineers figure out how to integrate the whole thing, and then you need the material scientists to figure out how to build these devices. So it really depends on what you like the most. I mean, if you like materials, you should do like, I would say, like, most of the people are physicists, I would say, but there is also a lot of RF engineers.
Awesome. We have a question from Keegan. How will quantum computing affect cybersecurity?
A lot. I mean, as of now, we don't have a quantum computer that is yet, I would say, Google says that they have like a 16 qubits device that is like better than a classical computer. It do just one thing though, and I think like just one specific algorithm. We don't have yet a quantum computer that can break all the cryptography codes that we have, but we're gonna end up there eventually, I believe. And that is a big issue, because as it was like saying at the beginning of my presentation, so a classical computer, if you want to hack something and you have like to figure out a code, for example, or a password. A standard computer does that sequentially. It tries each and every possibility one after the other. And that takes really long time, especially with the cryptography that we have right now. We're talking about billion years to figure out what is the right password. A quantum computer instead tries out all the possibilities at the same moment. And so to crack a cryptographic problem that we have right now, it probably is going to take it, I don't know, 10 minutes maybe. So it is a big problem. As soon as quantum computers are going to be available to everybody, we should change also the way we encrypt files and protect files. So.
Yeah, but maybe one thing I can add is that though quantum communication is very secure because each of these devices is unique in physical properties. So, it's very hard then to crack a quantum computer because there are some physical properties that are unique for that system.
Yeah, another thing that could be interesting, for example, whenever quantum computers are going to be available, all this thing about Bitcoins is going to be a big problem because at that point you can generate Bitcoins like with zero effort. So it's going to be a big problem.
I have a question from Lily. Are there any other ways to make it work other than making it cold? It sounds like this is a very hard thing to do outside of the lab. Is it possible for quantum computers to someday become reachable for common people?
So yes and no. I mean, it depends on the technology, first of all. And so the way we imagine quantum computing for the population is mostly like using a quantum cloud. So in a sense that it's going to be really complicated to have your phone that is a quantum phone, for example, a quantum smartphone is something really complicated. What, at least in the next, I don't know, 50 years, what we can imagine is that we're going to have like a really big dilution refrigerators, or many of them connected together, that host a really big quantum computer to which you can actually access with a cloud, something that Google or IBM are already doing. And I think that is going to be most likely the future. But I don't see, also because, I mean, the technology that we are developing, this superconducting qubit technology, is the most promising because we already know how to build these devices. Is really integrable. We can actually understand, we can actually do multiple qubits type of manipulation. We can connect qubits together with other type of technologies, such as, for example, ions, trapped ions, becomes much more complicated because we need really a huge magnet with these ions that are flying in. They get confined in a big magnetic field, and then you control them by lasers. So also that one is a really, really complicated type of scheme. So I would say that we didn't discover yet a technology that can be applied to build like personal PCs, laptops, or smartphones in with quantum computation possibilities. So we don't have, the only way that we can work with are these objects right now that needs to be cooled at really low temperatures or need really extensive type of infrastructure around to work with. So yeah.
Maybe one thing I can add here is that, here we are really at like stage 0 or 1, and like the computer that now we used to have and are really available to everybody a few decades ago were as big as a room. So, I think it is possible to think about some kind of scalability, maybe for the kind of environment this device work, very cold, or as Mattia was saying, like magnetic field is not something that you can bring at home. But I think we can imagine about some big fab or some big facilities, and then you can access through the cloud. So yeah, I think this is something that is reasonable.
Great. Keep taking questions. Is that okay?
Yeah, that's fine.
Okay. Or I didn't know if there's anything else you wanted to show, or.
I mean, we can show.
Walk around the lab.
Yeah, I can.
Sure.
Maybe it's better. So, just to give you a flavor, so for the dilution refrigerator that Silvia showed, that is behind this rack of electronics. So this is like the electronics that is needed to do experiments to control qubits. So there are really it's really expensive electronics, I would say. Maybe Silvia can comment definitely more than me on this. This is her area.
Yeah, so again, everything, energies are so weak, entangled, so you need to have, very low noise instrumentation to access the computer, because you don't want to have the noise, you already have a lot of things to deal into the cavity and the qubit, so you don't want to have external noise going in. And so this is why you need this kind of instrumentation. However, also there are ways that we can scale. So for example, these are kind of big instruments, and then there are kind of crates here in which you can plug many instruments in, and you can control many devices.
So then here there is this is like a test lab, basically, test bench. Then we have another dilution refrigerator that is down here. This is huge. This is actually much larger than the other one. And this is being commissioned, actually. It's not yet operational. But so this is probably has a capacity of double than the other one. So eventually what the Fermilab wants to do is to build up a really, really huge quantum computer with the architecture that we are pushing, that is based on these superconducting cavities, and build a dilution refrigerator that is bigger than that one, I would say. So
yeah, I think the plan is to make one that is 2 meters by 2 meters.
Yeah,
so,
it's actually it's pretty really huge, I would say.
You said 3 meters by 3 meters?
2 by 2. It's
2 by 2. Okay.
2 by 2, yeah, 6 feet by 6 feet.
Yeah.
Wow.
Like, and by 6 feet by 6 feet, it means the cold area where you can actually store your qubits. So you can imagine that there you can store probably, I don't know, 100 qubits. And if you do 2 to 200, you get how many states you can get inside there. And that is already like extremely powerful computer, much more powerful than the big cluster that they have, for example, at the CIA or NASA to do any type of calculation.
I have a question. How fast is this technology developing? Have there been any major breakthroughs recently? Are there any roadblocks you are currently working on?
So there are been like breakthroughs, as I said, like Google showed that for a specific type of algorithms, their device are better than a classical computer. That is what they call quantum supremacy. So simply that a quantum computer is better than a classical one. But they demonstrated that for just specific type of algorithm. So right now, the biggest effort that we are working with, and everybody in the world is doing, is actually figure out how to protect these devices and try to eliminate as much as possible their interaction with the external world, because that is the major source of what we call decoherence, where decoherence means that you are losing information. So as I was saying, you are basically flipping your state of the qubit from 0 to 1, not because you want it, but just because the qubit is interacting and is changing its state. And that is something that we don't want. So a lot of studies is being done in that direction. And that's why there is a lot of material science going on right now in the quantum computation world. This is in terms of hardware. In terms of algorithm, they probably already there. They could, in principle, if we can provide an hardware that is good enough, they could already solve really complicated problems. So I would say that we, the harder people, are behind compared to, are lagging behind compared to algorithm people. But because we are really fighting against something that is complicated to solve. So, and I would say like what we're doing here at Fermilab is already a breakthrough. So the idea is to use these specific cavities that we have where you can store information for 2 seconds. It's already a breakthrough, because typical Google qubit, for example, can store information for a maximum of 200 microseconds, which means that if you run an algorithm, you must be really fast to run it, because after 200 microseconds, you lose the information that was in that qubit. With our technology, in principle, you can store the information for 2 seconds. So we also did a breakthrough. We are still testing it, though.
A couple questions I'm going to combine. How heavy is the computer, and how many of these labs/computers exist?
How heavy is the computer? I don't know. I really don't know.
But you mean heavy like weight?
Yeah, how heavy in terms of weight, how much it weighs.
Yes, yes.
For example, I don't know. I mean, I think the dilution refrigerator cavities are light. I mean,
There are very small.
the smaller one probably, I don't know. I would say like 500 grams at top when they have all the instrumentation around. It really depends on the
Like
cavity.
10 ounces.
This is like really, really, really small, and I don't know. It's like probably 4 grams, 5 grams weight. The overall dilution refrigerator probably, I don't know, 100 kilos, something like that. So I don't know, with a dilution refrigerator full of cavities, I would say that probably you don't.
But it's not something that you move.
Yeah, exactly. It's like there, it's fixed. But so probably, I don't know, 500 kilograms where you are like super loaded with cavities, but I think nobody ever reached that weight. Probably 200 kilograms, 150 kilograms is already probably the maximum weight that this type of devices weigh. The devices, the computers weight. So I would say like right now there are like many places where they do this kind of experiments. Fermilab is one of those. Here in the Chicago area, there are many. So we have University of Chicago, Northwestern University, Argo National Lab. Again, ourselves. Then we have around the United States, really a lot. Yale, Google, IBM. There are many like Wisconsin Madison, for example, NIST, Boulder, Colorado, many around the United States. There are many in Europe, and I believe also in China they're starting doing things. But at the end, I mean, it's really a lot of groups they are working on quantum computation science in general, and because it's not only interesting in the sense of building a quantum computer, it's really interesting in a sense of like full fundamental physics, studying quantum mechanics. Is the first time that we can really manipulate quantum mechanical state and play with them. And that is like really attractive for a physicist in general.
I have, sorry, there's so many questions in the chat. This is great. Someone's asking, they must be familiar with our neutrino research. Could neutrinos be an issue in the future if when quantum computers become more common? Are they an issue for you now?
What do you mean an issue? That they can interact with the qubits?
I think that would be the question, yes.
I believe not. Those neutrinos, they really weakly interact with everything. You need to have like really heavy atoms, such as, I mean, liquid argon, for example, so that they can actually scatter and be detected. So neutrinos are not really an issue. What is actually an issue, though, is other type of particles that comes from the cosmos, such as gamma rays, for example, beta rays, alpha rays. So all this type of ionizing type of radiation that can actually strike the qubit and introduce dissipation and introduce so-called decoherence. So there might be some source of noise, if you want, coming from this cosmos, but I would say neutrinos are not one of those.
Awesome. And I'm checking the time, and I just want to add one last question that's actually from me. What are you most excited about, looking forward to as far as quantum computing and the work at the lab? Anything that you want to kind of share as we wrap up the session?
You want to start, Silvia?
Yeah, so I mean, we are very into the hardware. We, scientifically, we are very interested in building, the fastest and the most powerful quantum computer ever made. And, we are excited because we know that we have all the pieces to do this, but now we have to put them together. And then we are also excited because of the collaboration that we have. So, this is pretty diverse and international environment to work in and cross-functional. So, every day we learn about something different that is not exactly in our field, and we collaborate with, a lot of institutions that are also not based in US, and like Mattia and I, we are Italian, and there is a lot of collaboration with a lot of institutions around the world. This is actually an added value, in my opinion, because we need to bring diverse ideas all together to bring something so powerful.
Yeah, I totally agree with Silvia. I think that is like one of the best thing that happened in the lab in the last years, I would say, because we both were working in superconducting cavities, really interesting and important work. But quantum computation science seems like to be like the way to go because it has like a really high impact. And by doing research in this area, we could really think about changing what is going to be the future. So and be part of it in a really heavy way. So I think that is like the most beautiful thing that, of working in this environment. And of course, working at Fermilab is wonderful in general. So so yeah.
Awesome. Well, thank you both so much for taking time out of your day. I know I didn't get to everyone's questions. We could probably just sit here all day and kind of pick your brains for information. But thank you all for being here for our Quantum Lab virtual tour. Thank you to our tour guides, Silvia and Mattia. Really appreciate it. I know you're super busy trying to make all this work. So appreciate you being part of our virtual open house. And thank you so much. For those that were asking, I will have a recording of this available on the website. There's just some processing that needs to happen. So.
Okay. Right. I just want to add one thing. Stay tuned, and there will be a lot of internship opportunities, summer schools, and outreaching and so on. So we have a website at fms.canal.gov. We will publish everything there. So like there is undergraduate students or graduate students that want to be involved. We are planning a lot of possibilities for them.
Right. Yeah. Watch for internships. I can send it out to the list that registered. Happy to do that. Right. Thank you.
Thank you very much.
Yep. Enjoy the rest of your day.